Here is a quick tutorial to show you how to use some of the functions in the virtual neuron laboratory. Notice the legend is going to give you the different sodium and potassium ions, as well as the different voltage-gated and leak channels. This neuron is at rest. In the lower right-hand corner, you will see a box that says Show. Go ahead and click on the different boxes to show the different features. You can show all the different ions, the charges, the concentrations of sodium and potassium, and a potential chart. The potential chart is only going to show action potentials. So when you click on it and you haven't stimulated the neuron, you'll just notice that it is blank. But just keep in mind that a neuron at rest is going to be holding steady at about -70 millivolts. You also have a feature here so that you can zoom in on a region of this axon. This allows you to see more clearly what channels are open and what ions are moving across the membrane. Let's go ahead and stimulate the neuron. We can do this by clicking on the button Stimulate Neuron. When the neuron is stimulated, we can see that channels are opening and ions are moving across the membrane. Now if we click on Potential Chart, we can see that we had generated an action potential. The action potential goes to about +30 millivolts, followed by a hyperpolarization phase to about -90 millivolts, and then the membrane comes back to rest at its resting membrane potential of about -70 millivolts. Let's go ahead and slow down this animation so that we can see more clearly what's going on. We're stimulating our neuron once again. We're seeing that channels are opening. Let's zoom in to see what channels are opening. Once the membrane threshold of -55 millivolts is reached, we see a rapid influx of sodium through the voltage-gated sodium channels, causing the depolarization phase or rising phase of the action potential. At the peak of the action potential, which is around +30 millivolts, the voltage-gated sodium channels inactivate through a time-activated inactivation gate. The inactivation of voltage-gated sodium channels, along with the slower acting voltage-gated potassium channels, which do not inactivate, both contribute to the falling phase or repolarization phase of the action potential. During the falling phase or repolarization phase of the action potential, the sodium channels continue to be inactivated while the potassium channels remain open. Potassium ions continue to leave the cell, hyperpolarizing the cell to approximately -90 millivolts, which is the equilibrium potential for potassium. This causes the hyperpolarization phase or undershoot phase of the action potential. However, the voltage-gated potassium channels begin to close because the membrane potential is no longer depolarized. As these channels close, we see a return to the resting membrane potential of approximately -70 millivolts.